So this module is on surface flux integration. So far in the double integration, well, the surface integration part, we started with surface area, then we talked about surface integration itself, which was integrating some function as it varies over a surface. So just before we get to Stoke's theorem, we have to talk about one more extension of the concept, and that's where we want to talk about vector fields and surface integrations. Okay? And specifically, the concept here is, imagine we have a vector field, this is always the case, right? When we have a vector field, it's defined everywhere, and we want to then lay down a surface in this region where there's a pre-existing vector field. So this could be a flow field, could be flow of some fluid, could be electric field, could be whatever. Is defined everywhere in our 3D space. So sometimes it's pointing up, sometimes it's pointing to the left, sometimes it's pointing down, but there's some sort of vector field over this region. And then the idea is we want to say, okay, well, what if I throw a sheet or a net into the middle of this vector field? Okay, so it could be like this, okay? And it's kind of hard to see here, but what I'm going to draw here, so let's just imagine then that we've got this surface. Now this is not in the plane of the board, it's some 3D surface, which would have some projection, some shadow down in the XY plane, right? Also a shadow in the XZ plane and a shadow in the YZ plane. And what you want to ask is, okay, so I've got this sheet or net in this vector field. I want to look at every little location on this surface, and I want to ask the question, well, okay, so my vector field, let's say it was pointing in this direction, but I want to ask how much of the vector field is flowing through my surface perpendicular to the surface. So what component of the vector field is parallel to the normal of the surface? So if this defines my surface normal, okay, so if this is a sheet of, this is my net, okay, I've got some total vector field in space. I have a concept of a perpendicular vector to my surface. So I want to ask how much of this vector flow field is coming straight through the surface, not along the surface, but straight through the surface. Okay? And that's the same as asking what F dot this is. So F dot on this normal vector. Okay? How much of the vector field is parallel to the normal, and then I'm going to sum that up over the surface and do a surface integral of this thing. So before, when we did, like last module, we talked about surface integrals, and we had some function that could be temperature or power or whatever over a surface. Now, the function is going to be the component of a vector field perpendicular to the surface integrated over the surface. And this has got a special name. This is called flux. Okay? We often use the symbol, we don't always, but we often use the symbol capital Phi. Okay? But this is a flux integral. Okay? Flux integrals came up last year when you're doing first year physics in the context of electromagnetics and Gauss's law. We talked about the idea at that time, and we'll talk about this again, that if you summed up all the components of electric field perpendicular to a surface and did that over a closed surface, that was somehow related to the total charge inside that surface. It's actually going to yield to us divergence theorem, but we're not ready for that yet. Okay, but we were doing flux integrals in that context. So this is a flux integral. The integral of the vector field F, the flux of it through some surface S, is this integral. So you have to be given the vector field, you have to be given some surface, and once you have the surface, you can compute a normal vector, you calculate the dot product of the known vector field and that normal vector, you get some new function, then you convert this ds into x or y or z or whatever coordinate system you want, and you execute the surface integration. Okay, so that's what we're doing now. It's the same as what we've done before, it's just that now there's a step to arrive at the scalar function that we're integrating, and that's going to be this normal component calculation. Okay. Now, like usual, the easiest thing to do here is to start with an example. Okay, this is a pretty straightforward example, but not trivial. Okay, so this is from section, I think it's one of the examples in section 913 of the textbook. Okay, the problem says, okay, we've got some vector field, so you're always going to be given a vector field, right? Some vector field that comes from whatever physics situation you're trying to analyze. Okay, we've got some vector field. I'm going to say it's a function of x and y and z. Okay, and it is going to be, happens to be z times j plus z times k. Kind of a weird vector field. Okay, so it's just z times j plus k. Okay, so it's a vector field that has no x component, has only y and z components, and the size of the y and z components get larger the larger z is. Okay, we'll sort of sketch that. Okay, so I'll try to sketch it right here. Okay. X, this is y, this is z. So on the z equals 0 plane, the vector field is 0. And then as you go up in f, basically, if I just pick a point here, here the vector field kind of has no component, then it's got some component, then it's got a larger component, then it's got a larger component, then it's got a very large component. And the component gets larger the higher z is. It doesn't matter what x and y are, but it gets larger the larger z is. Okay, that's the idea. So they had this space, it still fills a space. For every x, y, z in this space, I can calculate this vector field. It happens not to depend on x or y, it only depends on z, and it happens to have no z component. So the vector field is always in the yz direction. Okay? But for us right now, all we really care about is that it equals z j plus k. So that's, I can't do a flux integral yet, I've just got a vector field. The question says, we've got this vector field, and we have some surface defined by, this is how it would be said, portion of the plane z equals 6 minus 3x minus 2y in the x greater than or equal to 0, y greater than or equal to 0, z greater than or equal to 0 region. This is often called the first octant. We've called it that in problems before. So basically, it's this cube of space in the positive y, positive x, positive z direction. Okay, and it's this plane. So this plane cuts this surface. So when x and y are 0, z is 6. Okay, when z is 0 and x is 0, y equals 3. So this is 6. This is 3. When z is 0, y is 0, x is 2. Right? 0 equals 6 minus 3x, so x equals 2. So the plane looks like this. This is 2, 3, and 6. Kind of I'm drawing this perfectly. Right? That's the plane. So it's this sort of triangular looking plane, and I just care about the part of it that's in the positive quadrant. Okay? And we're going to ask the question, well, what's the flux of this vector field over through this surface S? Okay? That's the problem. Okay, so the problem would say find the flux of F through S. That's how this would be stated. Okay, so if we're going to do this, let's just remind yourselves for a second here, what is flux, right? So flux, right, is the surface integral of, all right, F dot N ds. So what do we have to do? The first thing we have to do is build the integrand. Okay? Then we're going to have to decide what coordinate system we're going to do this in and what order we're going to do the surface integration, right? So we're going to compress this thing down, and is this surface a height over the xy plane, or a height over the xz plane, or a height over the yz plane? Remember, we always have those three choices. This case, we're actually going to consider this a height over the xy plane. Okay, so this defines the surface, this defines F. Okay? So the first thing we're going to do is find n. That may seem counterintuitive, but n we get from the surface, and once we have n, we take the dot product with f, and then we have our integrand, and then we proceed with the integration like we had before. Okay. Now, how do we find a normal like this? Okay. So I'm just going to erase this for a second. Well, I'm just going to erase this. I'll probably redraw that surface here. Okay. I'm just going to remind ourselves, we have our surface. So our vector field, right, was z j plus k. And our surface was defined by the plane z equals 6 minus 3x minus 2y in the first octant. Okay, that's what we got. Now, I'm actually going to redraw this thing just quickly here because we're going to refer to this. So this was 2, 3, 6. Okay, that's our system. So what I need is the normal vector to this surface. Okay, I need the normal vector to the plane. So the plane, this thing here, is a level surface. And a vector, the direction that is perpendicular to a level surface, is found by the gradient of that scalar function. So if I think of z as this function, okay, then what I want, well, sorry, this whole thing as a function, I'm going to write this, okay, as this scalar function equals, I'll get everything on one side, so I got 3x plus 2y plus z minus 6 equals 0. Okay. So 3x plus 2y plus z equals 6 is one level curve of this three-dimensional function, right? Now, this is just like when we talked about gradients earlier, weeks ago. So to find the direction perpendicular to this, I need to calculate the gradient of g. Okay? So the gradient to g, right, is the differential with respect to, the partial with respect to xi, so it becomes 3i, plus the partial derivative of this whole thing with respect to y, which is 2j, the partial derivative of this whole thing with respect to z, which is 1, k. This really doesn't matter, actually, but we keep it in there. What we generally do is you find your surface, you create a three-dimensional function for that surface without the constant, and then you take the gradient of that, and that will give you the vector perpendicular to the surface. Now sometimes the vector is a constant, sometimes the vector is a function of x, y, z. If the surface is a plane, then the direction perpendicular to that surface will always be the same, so it's a constant. When we do a surface, if I did a hemisphere or something, and there are problems like this, then we'll find that this gradient function is itself a function of x, y, z, because depending on where you are on the surface, the normal's pointing in a different direction, right? So they will find that through the gradient operation. Okay. So this vector is perpendicular to the surface. Great, but it's not a unit vector, right? So to get n, we have to look at the gradient vector divided by the magnitude of the gradient. Okay. So we normalize it. So simply put, then that's 3i plus 2j plus k divided by the square root of the sum of the squares of each component. So that's 9 plus 4 plus 1. Right? So square root 14. So this becomes 1 over square root 14 times 3i plus 2j plus k. Okay? That is our unit normal vector to this surface S. Okay? Now that we have this and we have f, I can calculate f dot n, and then we'll be ready to set up the integral. And then we'll be just repeating things we've done before. But this is the order you should go in. You have this whole thing, then you identify the function that defines the surface, you take the gradient of that function, then you normalize that gradient to get a unit vector, and now you calculate this. It's tempting to put this all into the flux integral and do it in one shot, and you shouldn't do that. I say it all the time. You should just do this in steps, small steps. Okay, so f dot n, right, would be, well, equals, okay, what's f? We have z j plus k dot 1 over square root 14 3i plus 2j plus k. Okay, so this thing looks like, okay, so there's no I component here, so there's no, this 3 is not by anything. So we will have, let's see, we'll have z over square root 14, that's out front. And then I'll have, so there's no I to that, then j dot j is 2, right? And then we have k 1. So this becomes 3z over square root 14. Okay. That is f dot n. Okay. It only depends on the magnitude of z, right? Which makes sense. Okay. So therefore our flux will be equal this surface integral of 3z square root 14 ds. So this is clearly 3 square root 14 surface integral of z ds. Okay. At this point, it's just like a surface integral we did a couple weeks ago, or a couple modules ago, right? Now what we have to do is just say, okay, well, so I've got this function z that's varying over s. Now we have to convert s into some height function over some region. And I'm going to consider it over a region r here on the bottom. Okay. So we're going to call that r. That's what we're going to do. Okay. So this surface here, this line here, right, is equal to our function when z equals 0. So it is that z equals 0. So this means that this line is 3x plus 2y equals 6. That's that line. And we're going to solve this for y. So y equals 1 over 2, 6 minus 3x, which is 3 minus 3 over 2x. So that describes this line here. Okay. So we're first going to integrate, we're going to consider this surface a height over this region. So that means that ds is going to be the square root of 1 plus the 2 partials. The partial of the surface height with respect to x squared and the partial of the surface with respect to y squared. So when we take this ds, we had this before, ds will be square root of 1 plus partial z partial x squared partial z partial y squared, right? dA. And dA is the area element of this guy r. Remember, if we're thinking of this, we think of z as a height over x and y as the surface, then this is the conversion from ds to dA. If we think of this surface as a height y over xz, then we'd have the square root of 1 plus the partial of y with respect to x squared, partial y with respect to z squared. Right? And there were 3 different versions of that. Okay. So what is this thing? This ds is square root 1 plus, well, what's the partial of z with respect to x? Okay. Minus 3. Plus partial of z with respect to y. It's minus 2. Oops. Grab my dA here. dA, so this is square root 14 dA. Okay. Now as it happens, and we talk about this in class a little bit, there are times, it's not all the time, but often there are times where the conversion of ds to dA has a factor that cancels out the normalization of the normal vector. It's not always the case, but it is often the case. It actually depends on a little bit what region we define to use. Okay? In other words, how we think of this integral. If we changed it, it wouldn't always be that way. We'd have the same normal vector, And if instead I did this integration over the xz plane, then they wouldn't quite cancel off. Okay. Now, so I found the surface, and I found n, and I took n dot f, and I've got this integrand, and I put that here, and now I've got a conversion of ds to dA. So now we're ready to, and I'm going to do this right here. Right? So my flux, right, is going to be equal, okay, and now I'm doing a double integral, right, over this region R. Right? I'm no longer doing the surface integral now. Now I've converted the surface integral into an integral, or a double integral over the region R. Okay, so I've got 3z over square root 14, and then I've got square root 14 dA. Right? So then we've got 14. So this is 3 double integral z, okay, and then I'm going to do, my dA is going to be dy dx, or dx dy. And the last thing I need to do is figure out the limits of integration. So the first thing I'm going to do is since I've already got z as the height of this, now what we're going to do is we're going to move and integrate, we're going to integrate y first, okay? So the limit, right, for y is 0 out to this line. So this integral for y goes from 0 to 3 minus 3 over 2x, right? The limit on x is 0 to 2. Right? Again, that was a choice, right? I decided we had z over x and y, got it. So then I have this 2D region in the xy plane. And then I have a choice. Am I going to get rid of y first, or am I going to get rid of x first? If I get rid of y first, I have to write y as a function of x as the limits of integration. So I look at y, and y goes from, well, starts at 0, but also goes up to a function of x. So function of x. Okay. Now, the other thing though is z. Z is, we're integrating on this surface. So this thing, so you put the definition for the surface, 3 over 2x, and then z is 6 minus 3x minus 2y dy dx. Right? Because when we're integrating on the surface, the value of z is given by that surface. Okay, so now it's easy. Now we're just doing it. We'll do this kind of quickly. Okay, well here, we'll do the first step here. So I'm integrating the first thing with respect to y. So this thing becomes, all right, so I got 3, 0, 2, then what, 6y minus 3xy minus y squared, so it's minus 2y squared divided by 2, so, right? And then we execute this at 3 minus 3 over 2x and 0, okay? And then when we're done, we'll have purely a function of x, and then we'll integrate that from 0 to 2. Okay, so our flux, right, becomes 3 times 0 to 2. Okay, and then we have, now the second term will all be 0, so we'll just have, we got 6y, 3 minus 3 over 2x, minus 3x, 3 minus 3 over 2x, minus y squared, minus 3 minus 3 over 2x squared, and this whole thing's with respect to x, right? When we do the 0, like minus the y at 0, every term turns out to be 0. So this surely should be this minus this minus this minus 0. Okay? But that's easy. Okay. Now, I'm gonna, just in the sake of keeping this, I think you can handle this polynomial extraction, okay? Okay, so if I just do a little bit of magic here, this is going to simplify down into a polynomial. It would be 3, 0 to 2, okay, 9x squared over 4 minus 9x plus 9. Okay. When we work all that out and simplify it down, this is what we're going to end up with. Okay, you can do that part. And then, so now we just do this with respect to x. So we have 3, and then we have 9 over 4, x cubed over 3 minus 9x squared over 2 plus 9x, 2 to 0. Okay, so this becomes 3, 9 over 4, 8 over 3 minus 9 over 2 times 4 plus 18 minus 0. Okay, so that becomes, so this is 3 times 18 over 3 minus 36 by 2 is 18 plus 18, so this is minus 18 plus 18. Cancel, cancel. This just becomes 18. What are its units? Depends. We've not been doing it in calculus. We're focusing on the calculus operations, right? We're not taking effort to keep the units of these things right. What this flux would mean, it depends on the nature of the vector field. If the vector field was, electric field, then we'd have some sort of electric field meter squared answer, right? Because we're summing up a field and whatever its units are, and a surface area as we sum it over the area of a surface. So it would tend to have units of m squared. Okay, so we would have some actual physical units if we worked this out, or if we had a real coefficient that helped us. Okay, that's it. That's it. That's a surface flux integral. Okay, in the note module that goes along with this little real-time lecture, I also do this another way. I show this where we did a different definition of this region. I think of this not as a y as a function of x, but I think of an x as a function of y, and I do it again and show you get the same answer. Okay, we've talked about those sort of things before. That's just a characteristic of surface integration. So what's important here, as we go back, is that we have a problem. It says calculate the flux of some vector field through a surface. That's how these questions are. Flux, vector field, surface. Okay, so we have our vector field, we carefully identify it. We have to identify our surface. Sometimes this is easy, sometimes it's not easy. If it's an intersection of curves, you have to visualize it. Okay, but I need some definition of this surface. Okay, and then what we do is we want to calculate the dot product of the vector field and the normal vector to the surface. So what we do is we calculate the normal vector. So we recast the surface equation in a general form where all the variables are on one side equals 0. Okay, that's what that general equation is. And then we say, okay, well, the surface is just a level surface of that. So we take the gradient of that thing. So we put everything on one side, z plus 3x plus 2y minus 6. Then we calculate the gradient of that. Okay, and that will either be a function or a constant. Then we normalize that, so divide it by its magnitude, the sum of the squares of each term squared. Then we have a normal vector. Once you have a normal vector, you take the dot product of the normal vector and the vector field to get the integrand for the flux. Okay? Once you have the integrand for the flux, then we're just doing a surface integration like we've done before. Okay? And then you decide, okay, well, what is my surface definition? Am I going to think of it as a height over xy or a height over xz, all that stuff? That choice guides you in how to convert ds to dA. It's the square root of 1 plus about 2 partials. Okay? You calculate that, and now you've got a double integral. Okay? And then you execute the double integral in the iterated sense, getting the limits correct, and you basically redoing things we've done before. So the only new thing now is the very first part, where you have a vector field. You have to identify a normal vector, calculate the dot product of those two, and then you're just doing a surface integral. Okay? That's surface flux integration.